Let us look at term-wise elementary operations on series. So first we will take up term-wise multiplication by a non-zero number. The convergence or divergence of a series does not change when the terms of the series are multiplied by a non-zero real number. So if a series is convergent, when we multiply it by a real number, all the terms, it remains convergent. And same way with divergence as well. So let's prove this. Given a series u sub n, let s sub n be the nth partial sum. Let t sub n be equal to c times u sub 1 plus c times u sub 2 and so on up to c times u sub n. So here, this is the nth partial sum. Now, t sub n is equal to c times s sub n, which is what we have done. So if the series u sub n is a convergent series converging to a finite value L, implies that limit as n goes to infinity of s sub n is equal to L. Okay, so if the series is convergent, then its partial sums also converge to L. Now, let's look at this. T sub n is equal to c times s sub n. Let's take the limit on both sides. We get limit as n goes to infinity of t sub n is equal to limit as n goes to infinity of c times s sub n is equal to, since c is a constant, we can take it out of the limit, which is equal to c times limit as n goes to infinity of s sub n, and limit as n goes to infinity of s sub n is L. Limit as n goes to infinity of t sub n is equal to c times L. The series c times u sub n is convergent and converges to c times L. So, which is what we have in this statement, that given a series, if you multiply it by a real number, non-zero real number, then it is also convergent. Similarly, in case of divergence, since t sub n is equal to c times s sub n and c is not equal to 0, if the sequence of partial sums of s sub n does not converge, then the sequence of partial sums of t sub n cannot converge. So, which implies if the series u sub n diverges, then this series also diverges. So that was term-wise multiplication by a non-zero number. Now let's look at the next elementary operation, term-wise addition or subtraction. So let's have two series u sub n and v sub n, both being convergent series. Now let s sub n be the nth partial sum, and limit as n goes to infinity of s sub n be equal to L, because we already know that these two are convergent. So the sequence of partial sums will also converge. Let t sub n is equal to the series v sub k from k equal to 1 to n, that is the nth partial sum, and limit as n goes to infinity of t sub n equal to m. Again, the series is convergent, that means partial sums are also, sequence of partial sums are also convergent. Then s sub n plus t sub n. Here we are handling both addition and subtraction. So that's why plus or minus t sub n is equal to nth partial sum of u sub k plus or minus v sub k. Limit as n goes to infinity of s sub n plus or minus t sub n is equal to limit as n goes to infinity of s sub n plus or minus limit as n goes to infinity of t sub n, which is equal to L plus or minus m. Hence, the sequence of partial sums of the series u sub k plus or minus v sub k converges to L plus or minus m. And therefore, the series k equal to 1 to infinity of u sub k plus or minus v sub k converges to L plus or minus m. So that was term-wise addition or subtraction. Now, addition or removal of finite number of terms from the start of an infinite series. So when we do that, the convergence or divergence of an infinite series does not change when a finite number of terms from the start of a series are removed. So first we will take care of removal part, and then we will look at the addition part. So given a series u sub n, which is a convergent series, let S sub n be the nth partial sum and limit as n goes to infinity of S sub n equal to L. Because it is a convergent series, that means its sequence of partial sums will also be convergent. Now let's remove m terms from the beginning. How do we remove it? Let T sub n be the nth partial sum after removal. That is, the series k equal to m plus 1 to m plus n of u sub k. So here what have we done? We are starting from m plus 1 term to m plus n. That means first m terms have been removed. T sub n is equal to S sub m plus n minus S sub m. So nth partial sum, that is T sub n, will be equal to the m plus nth partial sum minus mth partial sum. So we are subtracting the first m terms from S sub m plus n. So our T sub n will be equal to u sub m plus 1 plus u sub m plus 2 plus u sub m plus 3 and so on up to u sub m plus n, which is exactly what this is showing. Now, the sequence of partial sums S sub n is convergent, which implies that S sub m plus 1 sequence of partial sums converges with the same limit L. So S sub m is equal to u1 plus u2 plus u3 up to um is a finite series, therefore a fixed finite value. So taking the limit of this statement, T sub n is equal to S sub m plus n minus S sub m. So both sides we take the limit. So limit as n goes to infinity of T sub n is equal to limit as n goes to infinity of S sub m plus n minus S sub m will be equal to limit as n goes to infinity of S sub m plus n minus S sub m. Now this limit is L and S sub m is a finite fixed value. So L minus S sub m is the limit as n goes to infinity of T sub n. So therefore, the series n is equal to m plus 1 to infinity of u sub n is convergent. So we have shown that the convergence of an infinite series does not change when a finite number of terms from the start of a series are removed. Now let's look at divergence. If we have a divergent series, then the sequence of partial sums also diverges. And since T sub n is equal to S sub m plus n minus S sub m, where S sub m is a fixed value, subtracting S sub m from the sequence S sub m plus n cannot create convergence. So the sequence of partial sums T sub n is a shifted version of the sequence of partial sums S sub n, and a shift of a divergent sequence remains divergent. Hence, the sequence of partial sums T sub n is divergent, and therefore the series after removal of m terms is divergent. Now let's look at the case where finite number of terms are added to the series at the start. Previous case was removal. So given a series n is equal to m plus 1 to infinity of u sub n, let p sub n be the sequence of partial sums of this series. Let s sub m is equal to u1 plus u2 plus u3 and so on up to u sub m be a finite sum. Now, adding s sub m to the given series, what happens? Series k equal to 1 to infinity of u sub k is equal to s sub m plus the given series, which starts from m plus 1. Now let the sequence of partial sums of k equal to 1 to infinity of u sub k be q sub n. That implies that for all n in natural numbers, q sub m plus n is equal to s sub m plus p sub n. So the partial sums of the series n equal to 1 to infinity of u sub n are obtained by adding the fixed finite sum s sub m to the partial sums p sub n of the given series. And since s sub m is a finite fixed value, adding s sub m to the sequence p sub n cannot change convergence or divergence. The series n equal to 1 to infinity of u sub n is equal to s sub m plus the series n equal to m plus 1 to infinity of u sub n is convergent or divergent based on the convergence or divergence of the given series. That was term-wise elementary operations on series. Now, in case of removal, we are removing a finite number of terms from a given series. So that's perfectly fine. But when we are adding a finite number of terms to a given series, then we need to be careful. So in the addition of a finite number of terms, the terms added must belong to the same defining sequence as the given series. We can't just blindly take some other series which doesn't follow the formula based on which the given series is generated. If you found this session helpful, please do like, share, and subscribe. Comments, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now. Bye.